All right, inverses. The other day I recorded a lesson on inverses actually in this room, but for some reason the computer like dumped it. The file was corrupted or something, so I was not able to post it. So I'm going to have a double lesson today. The first thing I wanted to talk about then was a review of yesterday, or of actually Friday, and that was this stuff. Do you remember that there's two tests you can do? The vertical line test tells you if it's what? A function. But what does the horizontal line test tell you? It tells you about its inverse. The horizontal line test, which this one would actually pass, because when I take this horizontal line and I bring it down here, it doesn't ever touch twice. In this zone it gets close, but I think I drew it well enough. So it passes the horizontal. That means it's inverse. What? The inverse is a function. Good. So the other way was the vertical line test. That just tells you if it's a function. This one is a vertical line test passer, and it's also a horizontal line test passer. So its inverse would also be a function. So it's a special kind of function called a one-to-one function, if it can pass both the vertical line test and the horizontal line test. All right, next thing. How do you change a function into its inverse? There's a three-step process. See if you remember it. It starts like this. F of x equals, and let's say I say x squared plus 5. Then, how do you change it into its inverse? The first step, remember it? If you remember it, say it. Change it to y equals. Very good. Now, next step in the process. Flip x and y, because on a inverse, the inverse is where the x's and the y's completely reverse. So if you had the point like 2, 8, you'd have the point 8, 2 on the inverse. All right, so this changes to x equals y squared plus 5. And then if we had to solve for x, we'd already be done. So we're not doing that. We're solving for what? Everybody solve that for y, and you'll have the inverse. If 10% recalls of today's lesson is good enough for you, if you really only need to know 1 out of 10 things, then just listen. But if you actually want to remember anything serious, you better do this problem with me, because if you do it, about 5 times more likely to remember it. All right. Tell me how you started, Miss W. I agree. Oh, did you say 5? Okay, minus 5 is what I was thinking. Okay, and now what? Square root. All right, so then we get y equals, and this would be a classic mistake. Because, remember the absolute value thing? Plus and minus. Now, sometimes you don't use the -1 when you're doing the real world situation. In this one, you would actually. Let me prove it to you. Do you get that my original function is a parabola that's been shifted up 5? Does that look right to you? Is that a parabola shifted up 5? Does that make sense? Okay, so if I'm going to do an inverse, it's a reflection across this line. You remember that from Friday, or actually it was Thursday's lesson? So if it's going to be a flip across that line, do you get it's going to have a part of it that goes kind of like that? And it's also going to have part of it. How about this? If the reflection was just that, do you get it's missing part of it? It's like part of the parabola got chopped off. The other part of the parabola is like that. Now it's flipped across that line. Actually, I think I'm off a little bit here. Oh, I think I'm pretty much got it here. Okay, good. So now, let's look at this graph. Think about this. Isn't this just a square root function that's been shifted down? No, right 5? Square root function has been shifted right 5? All right. That tells me that I was off a little bit here. Square root function's been shifted right 5. It should be over there. And here's another square root function that's been shifted right 5, except it's got a negative in front of it. All right. So I'm sorry, I made a little mistake where I put it in the first place. These are hard to reflect across that line. But do you get that there's two parts, the regular part, the green part, and then this part, which is the upside down of it? And now, does that make sense that there's a plus and a minus in front of it? Because the plus of it is the square root of x minus 5. That's the one that was shifted 5 to the right. This one is negative square root of x minus 5. That's the same exact parabola, except it's flipped up, down. That's why there's two parts to this. Here's the parabola that's been shifted right 5, and here's the parabola that's been shifted right 5 and flipped. Do you get why these are a reflection across this line? Because if I had a point like 0 or 5 comma 0, that goes with 0 comma 5. See what I mean? And if it has a point on it like 6 comma 1, then this would have to have a point 1 comma 6. All right, still not graphed perfectly, but at least they're generally in the right spot now. All right. So those are inverses, and that's how you do a three-step process to find an inverse. So now, let's see if you can handle that all by yourself. Would you please try this one? I want you to take the square root of x minus 4 plus 6, and then do an inverse on this. Try to figure out, I've already done the first step. I changed the f of x into a y for you. Find the inverse for this function. I'll pause for a second while you try that. All right, here's what you should have done. You should have had x and y get reversed. This is x equals square root of y minus 4 plus 6. Then is each time from here on out, I'd start saying to myself, is y alone yet? Because that's what you're trying to do, is get y alone. So subtract 6. X minus 6 equals square root of y minus 4. Is y alone there? No. How do I get that square root off of there? Square both sides. Do I actually have to multiply this out? Not necessarily. Y minus 4. Is y alone yet? No. But if all I do, if I just add 4 to both sides, I'll have it alone. And look at this. It looks like a parabola. That's been shifted 6 to the right and up 4. Yes?
So would it be wrong if you like factored it out?
If you multiplied it all the way out, it would not be wrong. It's just extra work that you might mess up. Because like if a kid said, oh, this is x squared minus 36, they'd be making a couple mistakes as they were doing it. Really what you should have done is x minus 6 and x minus 6, and then first outside and said last. If you do it correctly, it's fine with me if you multiply that all the way out. It's just that this is vertex form, and there's nothing wrong with it the way it is, so no need. All right, what do we find? That's called the what? What did we just find? Rumpelstiltskin? The inverse. We found the inverse. Okay, that was a three-step process for finding an inverse. All right, now, one thing you can be sure, if you want to be sure that you have found an inverse, one way you can check it is, you remember how I was saying that if you, for instance, had a point like 2 comma 8, that the inverse would have to give you 8 comma 2? That'd be a smart thing to do if your life depended on whether these things were inverses or not. That'd be a way to check it. All right, so if I, for instance, put in an 8 for x here, I chose that on purpose so I'd have a nice square root. I'd have the square root of 4, which would be 2. 2 plus 6 is 8. Do you agree that 8 comma 8 is in this original function? I agree with myself. Okay, so then 8 comma 8 isn't really going to be one of those great points to reverse because it's 8 comma 8. But at least 8 comma 8 ought to work. Let's check it. To put in an 8 here, do I really get an 8 there? Let's check it. 8 minus 6 is 2. 2 squared is 4. 4 plus 4 is 8. It worked. Now, if that had been even better, if it had been like a 2 comma 9, and then we put in 9 comma 2, and it still worked. All right, but that's not an official proof that they are. And that's the last thing I need to teach you for today, is how do you officially prove that two things are inverses? Do you remember when I had to like prove something was odd or even? There was a rule that you had to prove. You had to prove f of negative x. Let's just remind you of that because review is really always a good thing. This is for the odd rule, and this is for the even rule. There's two different rules. One's odd, one's even. See if you can remember what they were. Write them down. I'll tell you if you're right or not, if you show it to me. The odd rule was one thing, and the even rule was something else. In a second, I want you to all turn your iPads my way. If you're not finished, you'll have to kind of turn it, as it's turned my way, you'll have to finish it. In a minute, not yet. I'm going to pause for a second. My microphone cut out for a second there. I wonder how long it was out for. All right, I'm just going to keep going here. Pause for a second. All right, so now g of x is supposed to be its inverse. I'm going to go back a couple slides and find the inverse I made. That was this guy without the 8's in it. And that was x minus 6 quantity squared plus 4. minus is weirdly high there. I'm going to move it. There. Okay. Good. There's my two functions. Here's how you would prove that they are equal to each other when you do g of f of x and f of g of x, and that they equal x. It's not nearly as complicated as it seems. First, you write out the statement f of g of x equals g of f of x, just like I just did. If you don't write that down, you cannot get the right answer. All right? Next, you draw a line down the middle right there. Then we're going to do f of g of x on the left side. We're going to do g of f of x on the right side. We're going to simplify them all the way down. And what do you think they should equal at the bottom here? Both of them should come out to what? X. Now, remember the other time we had a proof problem? It was all about the work. Because I know that if you're smart enough, you'll be able to say, oh, the answer is x equals x. But you have to prove this in here and here. You have to do these parts correctly. I know the answer is x equals x. That's what it has to be make this be inverses, and they will be inverses. So you have to prove it. So you have to show every step correctly. Your first step you'd have to show here is f of g of x. This is the one that got eaten by the f function. So I'm going to put this one right here, into the f function. All right, so square root of x minus 6 quantity squared plus 4, and then I throw the minus 4 on there. That's from this. And then plus 6. Now, it looks really scary, but it's actually very simple. Do you get that there's things that are going to cancel, like the plus 4 and the minus 4, and the plus 6 and the minus 6? You see what I'm talking about? It's all about the order you do it in, though. In a hard math problem, do you get that you're supposed to start on the inside of it? And therefore, I should start underneath that square root. And what gets canceled first? We're just simplifying. The 4s, yeah. They're gone now. Now you rewrite it without the 4s. Square root of x minus 6 quantity squared plus 6. Now, do you get that I have a plus 6 and a minus 6. If I cancel them at this point, I get the whole problem wrong because I'm doing it in the wrong order of operations. Do you get I have to finish up with what's underneath the square root first? Do you get that the squared and the square root are going to cancel each other out? And now I rewrite it again, simplified. X minus 6 plus 6. Now can you see that the plus 6 and the minus 6 are right next to each other and therefore can be canceled? And what does it simplify to? X, just like I thought it was gonna. All right, so that was f of g of x. Now with my red pen, I am going to write out what g of f of x is. F function needs to go into the g function. That means this guy needs to go into there. So now I take the g function right here, and I'm going to write him without the x. I'm going to put an empty spot where the x is. So I'm going to put empty spot minus 6 squared plus 4. Why did I do that? So that now it can eat the f function. And the f function goes into its stomach right there. And the f function then goes right here. Square root of x minus 4 plus 6. I just put the one function in the other function. Okay, so now, where do you start hard problems? One word answer. Starts with I. Come on. Inside. Okay, so I start on the inside, which is right there. And now what is going to get canceled first? Does it look like on the inside that the 4 and the negative 4 can cancel? No, they're not on the inside. What's on the inside that can cancel? The 6's. So they're gone. And now I can write it with the square root of x minus 4 squared, because the 6 is canceled, plus 4. And now, again, if a kid right here cancels off the 4's, no, not right. Why? What has to cancel first? The square root and the squared. Okay, good. Now you're catching on. X minus 4 on the inside plus 4. And now the squared and the square root are gone. Final answer. Do the 4's cancel at the end there? Yes, they do. So the answer is x, just like I hoped it would be. And I have proven that my two functions are inverses. I know that seems really difficult. Most people get this problem right when you see it again on the test. Okay? Pretty much you know, I think by now you figured out that everything we teach you is probably going to show up on the test at some point. Okay? And this is one of those that looks scary, but almost everybody gets this right. Common mistakes, people forget what the formula is, but if you just remember it's f of g of x equals g of f of x, you don't even have to have the equals x at the end, but you do have to have it at the bottom here. They have to come out equaling x at the bottom. All right? So now, see if you really learned anything. I'd like you to make a new page or scroll up far enough so you can't see anything else on your page. Write the formula again for telling if two things inverses are really inverses. And this is going to be f of x. And this is going to be g of x. I want you to tell me if they're really inverses or not. Just feeling like they're inverses is not good enough. You have to have shown that f of g of x is equal to g of f of x. Hopefully you already wrote that. Draw a line down the middle. Pause for a second while you try that. All right, so here's what you should have done. You put the g into the f function. This goes into that, so I'm going to take this function right here and write it with the empty parenthesis, square root, empty parenthesis, minus 4. And in the empty parenthesis, I drop in the x squared plus 4. Now, where do you start? You start on the inside. So if I cancel the square roots right now, I get the whole answer wrong, because I got to start on the inside. You should have started by getting rid of those 4's. And then what's left after you get rid of the 4's? Square root of x squared. And then you can get rid of that. This is all about the order of operations. You got to do it in the right order. Now I can simplify it to x. There you go. Raise your hand if you did that side right. Okay, good. The other side, the f goes into the g, so I take the g function and I write it with an empty spot where the x used to be, and I drop in this square root of x minus 4. And now what has to happen first? This one's a little trickier. Got to start on the inside, and if it's in there, I can't cancel the 4's. So I go squared and square root, cancel x plus, or x minus 4 plus 4. And now I can cancel the 4 and the minus 4, and I have x. X came out, and x came out. Were these two things that I gave you inverses? Yes, and you have proven it by showing what we showed. Okay? That's how you do today's stuff. Yes? It's a good question. I can tell you that almost every time it'll be an inverse. So if I ever got an answer that was showing they were not inverses, I would do it again and make sure. Okay, it's kind of like that kind where I was telling you, generally we either shade on the inside or shade on the outsides, and it's usually like that, but I can't promise it. It's like that. I can't promise that these are going to be inverses, but 9 times out of 10 they are. That's why we can't just accept an answer of x equals x. You've got to show us the steps in here of why it's x equals x, because it's pretty much always going to come out to x equals x. And I'm throwing in the pretty much because I don't want to promise it, because you never know. All right. There's your new stuff. Now let's do the first couple with, I'll do the first couple with you. Why don't you go find it? It is called 1.5.2, and it looks like this. All right. So here's find the inverse and state the domain and range of the inverse. Oh, that's something we didn't talk about before. I'm glad we're doing these, because we haven't talked about domain and range again. We did talk about it on Thursday, but so first thing I would do is domain and range. That'll keep you from forgetting that you don't do the domain and range of the actual inverse. You do the domain and range of the original problem, and then we flip them. All right, what is the domain of this puppy? If I were to graph it, sometimes that helps me. It's got a y-intercept of 3, and it has a slope of 2. So it looks something like that. Do you agree it goes from negative infinity to positive infinity in both directions? I'm going to pause for a second. Okay, we settled a little bit of a tech issue there. So now domain is from negative infinity to positive infinity, or otherwise known as all reals. The range, how low to how high, also all reals. So when I'm all done with this answer, I need the domain and range of my inverse function, which will be down here. And its domain and range, I don't even want to look at the inverse to get the domain and range. I just want to reverse these. So of course, if I reverse them, it's still all reals and all reals. But the domain is becoming the range, and the range is becoming the domain. Okay, remember that from before? That's really important part 2. Okay, now let's do the 3-step process. Y equals 2x plus 3, and then reverse the x and the y. X equals 2y plus 3. Then you subtract 3 from both sides. X minus 3 equals 2y. Then you divide by 2. And could you say x minus 3 divided by 2? Yep. Or you could have said x over 2 minus 3 over 2. Okay, so there's my function, or my inverse, right there. And it would have, what? Question? It's always a good idea to put in these parentheses, but it is not required to put in those parentheses. All right. 1 and 2 weren't very tough ones. I'd like to do a tough one with you. So let's skip down to number 3. I'm warning you, this kind's tough, and you have to know how to do it. All right, so let's do the domain and range first. Domain and range. I wish I could do this with a picture, but I can't, because I'm not always going to know what the graph looks like on this puppy. So then you have to think it through from the algebraic perspective. Domain means everything works except. What's the one thing that doesn't work on this guy? What would crash this function? Positive 1. Positive 1 would crash this function. So all reals except 1. I'm going to make that a number line. I like to do it that way. There are multiple ways you could do it. Everything except 1 is my domain. How about the range? Do you remember me telling you that the range is like how low to how high, and what stops you on your way from low to high? Asymptotes that go this way, which are horizontal asymptotes. Horizontal asymptotes are y things, right? And Bob tells you why. So is this bigger on bottom, bigger on top, or same on both? It's the same on both. So it's a y equals a ratio, and the ratio would be 1 to 1. So it's y equals 1 is my asymptote. So looks like it's the same exact thing. Everything works except 1. So again, the range is not, we're not doing what's on the bottom here. It happens to be the same. This one was a same on both, and that's a ratio. And it happens to be a 1 and a 1 here, and so it's a, that's why it's y equals 1. You don't use the denominator for that kind. It just happens to be the same this time. All right, cool, got our domain and range done. But that was for the original. Since they're identical again, the domain and range of the inverse are everything except 1. So I'm going to write that this way this time. You do need to be able to write your answers in interval notation. Oops, union in there. There we go. And now, that was just the relatively easy part. Now we've got to do our three-step process. Y equals x plus 1 over x minus 1. Reverse them, x equals y plus 1 over y minus 1. Then, do you remember me saying anytime you're trying to solve any equation that's got a fraction in it that you should get rid of and clear the fractions? So how am I going to clear the fraction here? Times by y minus 1. Times them by y minus 1 on both sides. So I have x times y minus 1 equals, those two will cancel, y plus 1. Is it solved for y yet? No. You got to get the y's together on the same side first. So this is xy minus x equals y plus 1. Y's still are not on the same side. I'm going to do a tricky double step here. I'm going to get this y over to that side. Xy minus y equals x plus 1. Now the y's are both on the same side. This is where I need somebody smart to figure out how to combine those two. You can use a little saying that I always repeat over and over again. If you can, say it, the whole thing. If you can factor, you should. Can you factor this on the left side? Yes, you can. So you should. Y comes out, you got x minus 1. Is y alone yet? Nope. Keep asking yourself that. Is y alone yet? I got to divide by, use green, shows up better on black. Dividing by x minus 1 on both sides. And now y is alone, and there it is. X plus 1 over x minus 1. Isn't that bizarre? It's the same as the original. X plus 1 over x minus 1. X plus 1 over x minus 1. That would have blown your mind if you had gotten that answer on the test. How could that be? Could it be that when you reflect it over the line, y equals x, that it ends up in exactly the same place as it was in the first place? Yep. So imagine for a second it was like this. And then you reflect it across the line y equals x. You see how the reflection will go right on top of where it used to be? So, moral of the story, when you get an inverse, you could get the original function back. It's possible. Yes? Nope. Because if you move it slightly, yeah, if you move it slightly, you can move it to a place where it won't reflect on top of itself. Okay. It's a good assumption, but I'm telling you that would not always be true. All right, so that was a tough one. I feel bad that I took away the only one that you have, but I did. If you show your work really thoroughly on it, then you'll learn from it. But now we've got a few left here on your homework that are, let's see here. Proving. These are the prove kinds. 7 and 8. Prove this is an inverse of that. And there's enough of them that, in my opinion, you guys could skip 11 and 12 and be, you know what, no, I'm not going to do that. I'm going to skip 10 and 12. Skip problems 10 and 12 for tonight's homework. And that'll keep it reasonable sized. And that's all I have for you for today.